Okay, so here's my first attempt at this. A question came in about when to use an end behavior model. If I'm interpreting this question correctly, can you use it just any time or there's certain times? So questions 17 and 18 from the last homework were my attempt to distinguishing between the two strategies here. Here, watch this. Look at that. So they both have the same function in here, but this one, the limits as x approaches 2, and in this one is what's going on as x approaches infinity, which is to say as far out to the right on the x-axis as you can imagine. When x is 2, all these parts matter. You can't ignore any of them and just scrub down to the leading term. If x is 2, for instance, that piece right there gives you 4. That piece gives you 2. That piece gives you -6. That's the most significant piece in the numerator there. You can't ignore it. So everything matters. And so when you do direct substitution, you put it into everything, and you get the 0 over 0, and then you proceed to try to factor and find the matching factors that produce either the 1 or in this case the -1. So here's our Fatah Bop strategy. But down in 18 here, now we're looking when x is positive infinity, when x is the biggest number you can think of. And if you take the biggest number you can think of, and even one that's not all that big, say 1,000,000, if x is 1,000,000, this piece right here is 1,000,000,000,000, because we just square 1,000,000. That's a pretty big deal. And then all of a sudden 1,000,000, just another 1,000,000, that's a relatively small value here. And then this -6 is just absolutely trivial. So when x becomes infinitely big, almost all the value becomes concentrated in these largest terms. So it's at these infinity limits that we can strip things down and just focus on the end behavior model, and the end in end behavior is the ends of the x-axis. So we got a limit at infinity. I'm going to take the end behavior model of this guy. I'm going to keep the x squared from the numerator and the negative x squared from the denominator. X squared over x squared is a 1, except when x is at 0, then it's undefined. But man, at positive infinity, we are nowhere near 0. So we can just call this x squared over x squared a 1, but in fact it's going to be a -1. And at positive infinity, this thing is just sort of settling in towards -1. So that is what I think addresses the question. At least I hope it does. I put two others on here for other reasons. These are just things that people are missing at higher rates than I would have expected. 20, there's just another. Here we are, instead of positive infinity, the limit's at negative infinity. But we're still talking about ridiculously large numbers. And ridiculously large cubed plus 64, that 64 is negligible. So we're gonna end behavior model the numerator and just make that x cubed, and we'll end behavior model the denominator and just make that x squared, and an x cubed over x squared simplifies to x. And then what is the limit as x approaches negative infinity of just x? You really could just direct substitute this. You could put in negative infinity and get negative infinity, or you could be a little bit fancier here and say if you had the line y equals x, what happens to the height of this line as x becomes increasingly negative? Well, the height of this line is becoming increasingly. It's just heading to negative infinity. So that limit right there is negative infinity. And then one of the subtle things from the second homework that I was most worried about, and it's been kind of hit or miss with whether or not people have it. So 23, it's a limit as x approaches negative infinity. So we're going to end behavior model again. And out towards infinity, that little +3, the fact that it's under the radical doesn't affect it. It doesn't matter. It's trivial stuff when it's paired with infinity squared. And so your end behavior model is gonna reduce the numerator to, well, it's gonna keep the numerator at 2x. The denominator, instead of the square root of x squared plus 3, will just become the square root of x squared. And if you square something and then take the square root of it, you don't necessarily get that number. If the number's positive, you get that number. But if the number's negative, this filter of the square root, which makes everything positive, it makes everything positive. So you don't get x, you get the absolute value of x. And the absolute value of x, sometimes it's x. If you were out at positive infinity, the absolute value of x would be x. But if you put a negative number, big or small, if you put a negative number into an absolute value function, you're not going to get that number. You're going to get the opposite of that number. So for instance, if I were to take the absolute value of -3, it's going to ultimately be 3, which is not -3. It's the opposite of -3. Okay, so the upshot of this, and I hope this is okay, is if you have a limit at -infinity of the absolute value of x, you simplify that into the opposite of x. X's cancel, leaving behind a -2, and at negative infinity, what's the height of the line y equals -2? Well, the height of it is -2. So what that says is this function right here. If you get all the way out to the left on the x-axis, the height starts settling in at a height of -2. So our limit as x approaches negative infinity of this function would be -2. All right, we are now at 6 minutes and 50 seconds. So I'm gonna get out of here and see if I can figure out how to share this thing.